In this video, we're going to talk about how to use the common log to solve some real-life problems. So remember, we talked about growth and decay equations in the exponential functions unit. Remember, we had different types of formulas to use depending on the type of information that we were given. And so you're going to find this formula chart very useful as we work on solving these equations because now we can use logarithms to find unknown values in the exponents. So let's start off with this example. It says the population of a town is 5,000 in the year 2010. Its population increases by 12% each year. After how many years will the town have 16,000 residents? Let's look at the important information here. So we have a town that starts with 5,000 people in 2010, and then it increases by 12% each year. And we want to know after how many years will the town have 16,000 residents. So the first thing we need to do is identify the formula. Since we see growth with a percentage, we're going to use this formula right here, this y equals a times 1, and then we're going to do plus r since it's increasing to the t. Let's now identify our variables. So remember, y is the final amount. So this town is going to end up having 16,000 people, but it's going to start off with 5,000 people. The growth rate is 12%, so we're just going to go ahead and change that to a decimal. That is going to be 0.12. And t here is our unknown value. So what we're going to do is substitute this information into the formula. So we have 16,000 equals 5,000 times 1 plus 0.12 to the t. So let's simplify this a little bit. We have 16,000 equals 5,000 times 1.12 to the t. So now we need to go ahead and isolate that exponential term. So I'm going to go ahead and divide both sides by 5,000. So that's going to give me 16,000 over 5,000. So the key to solving these problems is to not use your calculator until the final step because we want to avoid rounding errors. So we're just going to leave everything as it is and then work on simplifying once we type it all into our calculator. So now to solve this, what I'm going to do is I'm going to go ahead and take the log of both sides. So this gives me log of 16,000 over 5,000 equals the log of 1.12 to the t. Now we can use the power property to go ahead and bring that t down in front. So we have the log of 16,000 over 5,000 equals t times the log of 1.12. Now in order to isolate t, I'm going to go ahead and divide both sides by the log of 1.12. Remember, I need to do that on both sides of my equation. And so now we've successfully isolated t, so we're just going to go ahead and approximate this value using our calculator. So when we type this into Desmos, we're going to do log of parentheses and divided by 5,000. And then we're going to make sure and close the parentheses before we do divided by log of 1.12. So Desmos told us the answer was 10.26 approximately, so we're just going to go ahead and round to the nearest tenth, which is about 10.3. And in this case, our units are years. So now you can go ahead and pause the video and try doing this example on your own. So here we have bacteria in a petri dish that are doubling every hour, and the population is initially 350 organisms. We want to know how long it'll take the population to reach 6,000. So since we have doubling here, we're going to use this form of the equation y equals a times b to the x. So y is the final value, which is 6,000. A is the starting value, which is 350. And then the doubling means our b is going to be 2, right? Because that's our growth rate. When you set up our equation, we have 6,000 equals 350 times 2 to the x. To isolate the exponential term, we divide both sides by 350. And then we go ahead and take the log of both sides. So we have the log of 6,000 over 350 equals the log of 2 to the x. We bring down the x in front. And so that gives us the log of 6,000 over 350 equals x log 2. Then go ahead and divide both sides by the log of 2 in order to isolate x. So to solve this problem now, we're going to do log parentheses 6,000 divided by 350. And remember, arrow to the right, close the parentheses before we do divided by log of 2. So you can see the answers here, and we're going to round that to the 10th place. So that's about 4.1 years. So now let's try this example here. It says Susan invests $8,000 in an account that So let's try this example. It says Susan invests $8,000 in an account that earns 5% annual interest compounded quarterly. How many years will it take the balance to reach $10,000? So whenever we have compound interest, we want to go ahead and So now let's try this example. It says Susan invests $8,000 in an account that earns 5% annual interest compounded quarterly. How many years will it take for the balance to reach $10,000? Whenever we have compound interest, we want to use the formula y equals a times 1 plus r over n to the n times t. So I'm going to go ahead and write out that formula. And so in this problem, it says Susan invests $8,000 in an account that earns 5% annual interest compounded quarterly. How many years will it take for the balance to reach $10,000? So we want to use the compound interest formula to solve this problem. And so that means we have y equals a times 1 plus r over n to the n times t. So the y is going to be our final value, which is $10,000. A is going to be the starting value, which is $8,000. And then R is going to be the percent rate of change. So here we have 5%, which we're going to convert to a decimal. So that's going to be 0.05. N is going to be the number of times it's compounded. So if it's quarterly, that means our N is going to be 4, right? Because she's going to get interest 4 times a year. And then T is going to be our unknown value. So we're going to go ahead and substitute into this formula. So we have 10,000 equals 8,000 times 1 plus 0.05 over 4 to the 4 times t. Okay, so now we want to make this a little bit more simplified. That 1 plus 0.05 over 4, I'm going to go ahead and use my calculator to make that a little bit neater. When we do that on the calculator, that's going to turn into 1.0125. So this is now going to be 10,000 equals 8,000 times 1.0125 to the 4t. And now I just go ahead and solve this. So I'm going to start off by dividing both sides by 8,000 to get that exponential term by itself. And so that's going to give me 10,000 over 8,000 equals 1.0125 to the 4 times t. So now we've isolated the exponential term, so I'm going to go ahead and take the log of both sides. So I have the log of 10,000 over 8,000 equals the log of 1.0125 to the 4t, okay? So now we go ahead and bring the exponent down in front using the power property. So we have the log of 10,000 over 8,000 equals 4t times the log of 1.0125, okay? So now we need to isolate everything except the value of t. So we're just going to go ahead and divide by 4, and we're also going to divide by the log of 1.0125, right? That way we can do it all in just one step. So I have to do the same thing on the left side. So I'm going to divide by 4 log 1.0125. And now you can see here I've isolated t. So I'm going to go ahead and go to my calculator and figure out what the approximate value of t is. So here what I'm going to do now is type log parentheses 10,000 divided by 8,000. And then go ahead and close the parentheses and then divide by 4 log 1.0125. Okay, and the problem asks us to round to the nearest 10, so this is going to be approximately 4.5 years. So we have approximately 4.5 years as the value of t. Now you can go ahead and pause the video and try doing this example on your own. Since Joseph bought a car for $16,000, that's going to be our starting value. The value of the car depreciates and we're given our percentage. So we're going to go ahead and write this as y equals a times 1 minus r to the t. After how many years is it worth 7,000 means our final value is 7,000. So we have 7,000 equals 16,000 times 1 minus 0.3 to the t. We start off by going ahead and dividing both sides by 16,000. And then we have, this is equal to 0.7 to the t, so we need to take the log of both sides. We use the power property to bring down t, and then we go ahead and divide both sides by the log of 0.7. Now we can go to our calculator to go ahead and evaluate this. So now we're going to use our calculator to go ahead and evaluate this. So we have the log of parentheses 7,000 divided by 16,000. And then arrow to the right, close the parentheses, divided by log of 0.7. You can see this is approximately 2.3 when we round to the nearest 10th place. So there's one more application of exponential decay I want to go over with you, and this is called radioactive decay. So it's whenever you have a radioactive substance, there's something called a half-life, which is the amount of time it takes for half of the substance to decay. We're given this formula here, which is what we can use to calculate values in this type of. So let's look at an example. It says the sample originally contains 40 grams of a radioactive isotope. The half-life of the substance is 3 days. After how many days do 16 grams of the isotope remain in the sample? So when we're talking about radioactive decay, we want to use this formula A equals A naught times 1/2 to the T over H. A is going to be the final value. So here we want to know how long it takes to end up with 16 grams. A naught is the starting value. You can see here we start off with 40 grams of the isotope. 1/2 is there because we're talking in terms of half-life. T is the amount of time, and that's what we're trying to figure out. And then H is the half-life. Okay, so here it tells us that's 3 days, and that's the amount of time it takes for the substance to decay by 1/2. Let's go ahead and substitute this all into our formula. So we have 16 equals 40 times 1/2 to the T over 3. And let's go ahead and start off by isolating the exponential term. So I'm going to divide both sides by 40. So I'm going to say that 16 over 40 equals 1/2 to the T over 3. And if you don't like that 1/2 being like that, you can actually go ahead and convert that to a decimal. So I'm just going to make that 0.5. So this is 0.5 to the T over 3. I'm going to go ahead and take the log of both sides now. So I have the log of 16 over 40 is equal to the log of 0.5 to the T over 3. And the thing to keep in mind in here is that T over 3, all of that is the exponent, so I'm going to bring all of that down. So I have the log of 16 over 40 is equal to T over 3 times the log of 0.5, okay? And now I'm going to go ahead and divide both sides by the log of 0.5, so I can just go to my calculator. So when I divide both sides by the log of 0.5, I have this value is going to be equal to, well, the log of 0.5 cancels, and that's going to give me the value that's approximately T over 3. So once I go to my calculator, I'm going to be able to say that T over 3 is approximately whatever the log of 16 over 40 divided by the log of 0.5 is. So what I'm going to do in my calculator now is do log parentheses 16 over 40, and arrow to the right, close the parentheses, and then I'm going to divide by the log of 0.5. And you can see here that's approximately 1.3219. So now I know that T over 3 is approximately equal to 1.3219. And all I need to do now to solve for T is to go ahead and multiply both sides of this equation by 3. And so that's going to tell me that T is approximately equal to, I'm going to use my calculator for this now, so 1.3219 times 3, and that's about 3.9657. The problem asks to round to the nearest day, so that's going to be approximately equal to 4 days. So remember, exponential equations can be used to model many real-life situations. If there's an unknown value in the exponent, you can use logarithms to help you determine the missing value.